Welcome everyone to this video on transformers. Today we'll take a deep dive into understanding how the transformer architecture revolutionized natural language processing. I'll be walking you through the encoder-decoder architecture, the attention mechanism, and how these concepts form the foundation of modern large language models. By the end of this session, you'll have a solid understanding of why transformers replaced RNNs, and how they power models like GPT, BERT, and Claude. Let's start with why we needed transformers in the first place. When transformers were introduced in 2017, RNNs, particularly LSTMs, were the go-to architecture for sequence modeling. But RNNs had two critical problems. First, sequential processing. Each word had to be processed one after another. You couldn't parallelize this, which made training incredibly slow on modern GPUs. Second, the vanishing gradient problem caused long-distance context loss. Information from the beginning of a sentence would degrade as it passed through the recurrent chain. Imagine trying to connect the subject at the start of a paragraph with a pronoun at the end. RNNs struggled with this. Before diving into transformers, let's understand the encoder-decoder paradigm that they're built upon. The encoder reads and compresses the input into a fixed representation. Think of it as understanding and summarizing what was said. The decoder then takes this compressed representation and generates the output step by step. This architecture can be implemented with different building blocks. RNNs had the bottleneck issue we discussed. CNNs could parallelize, but had limited context windows. Transformers solved both problems with attention. Now here's where everything changes. The paper Attention is All You Need by Vaswani and colleagues at Google introduced transformers in 2017. The key innovation was simple but profound. Keep the encoder-decoder structure, but replace recurrence entirely with attention mechanisms. This enabled two game-changing capabilities: parallel processing. All words can be processed simultaneously, and direct connections. Any word can directly attend to any other word, regardless of distance. No more information loss over long sequences. No more sequential bottlenecks. So why did transformers become the dominant architecture? Let me give you the numbers. Training speed improved by roughly 100 times because we could fully utilize GPU parallelization. Long-range understanding became possible. A word at position 1 could directly connect to a word at position 1000. And critically, transformers scale beautifully. More data plus more parameters consistently yields better performance. This scalability is why every major language model today, BERT, GPT, T5, Llama, Claude, is built on the transformer architecture. Let's look at the high-level architecture. The transformer maintains the encoder-decoder structure. The encoder takes input, say an English sentence, and produces a matrix of contextual representations. Each word gets a vector that captures not just its meaning, but its meaning in context. The decoder takes these representations and generates output iteratively, perhaps a Spanish translation. Both encoder and decoder consist of stacked layers, 6 in the original model. Each layer refines the representations further, enabling increasingly sophisticated understanding. Let's break down the encoder workflow step by step. First, input embeddings convert tokens into 512-dimensional vectors. These vectors capture semantic meaning. Similar words have similar vectors. Then positional encoding adds position information using sine and cosine functions. This is crucial, because without recurrence, the model has no inherent sense of word order. Multihead self-attention is the core operation. It connects each word with every other word, computing query, key, and value matrices. Finally, a feed-forward network processes each position independently, adding nonlinearity and capacity. Each step includes residual connections and layer normalization for training stability. Before we go deeper, let's address a fundamental question. How do we convert text into numbers that neural networks can process? This is tokenization, splitting text into smaller units and mapping them to IDs. Word-level tokenization is simple, but creates huge vocabularies and can't handle new words. Character level keeps vocabulary small but loses semantic meaning and creates very long sequences. Subword tokenization, methods like BPE and wordpiece, gives us the best of both worlds. Unhappiness becomes unhappy. Meaningful units with manageable vocabulary size. Input embeddings are the first transformation in the encoder. Each token gets mapped to a 512-dimensional vector. These aren't random. They're learned during training to capture semantic relationships. Similar words end up with similar vectors. The embedding for king minus man plus woman approximately equals queen. These embeddings capture rich semantic structure. This embedding layer only operates at the bottom of the encoder. Upper layers receive the processed output from layers below. Positional encoding solves a critical problem. Without recurrence, how does the model know word order? The solution is elegant. We add position information directly to the embeddings using sine and cosine functions at different frequencies. Each position gets a unique encoding. The values range from -1 to 1. Different dimensions use different frequencies. This approach generalizes to any sequence length. We don't need to train on specific positions. The encoder stacks multiple identical layers, 6 in the original transformer. Each encoder layer has two main components, multi-head attention and a feed-forward network. Both components are wrapped with residual connections and layer normalization. This helps with gradient flow during training and enables us to stack many layers without degradation. As data flows through these layers, the representations become increasingly refined and context-aware. Now we reach the heart of transformers, multi-head self-attention. The core idea is that each word can attend to, or look at, every other word in the sequence. This enables the model to understand context regardless of distance. For each word, we compute 3 vectors through linear transformations. Query: what am I looking for? Key: what do I offer? Value: what information do I carry? We do this in parallel across multiple heads, 8 in the original model. Each head can learn different types of relationships. One might focus on syntax, another on semantic similarity. Let's walk through the attention computation, step by step. First, we compute attention scores by taking the dot product of query and key matrices. This creates a score matrix, showing how much each word should attend to every other word. Higher scores mean stronger attention. If the query for it has a high dot product with the key for cat, the model is learning that it refers to cat. This is the fundamental operation that allows transformers to capture relationships across the entire sequence. The raw attention scores can be very large, which causes problems during training. We scale them down by dividing by the square root of the key dimension. This is the scaled dot product attention. Why? Large values pushed through Softmax produce extremely peaked distributions, leading to vanishing gradients. Scaling keeps the values in a range where gradients flow well. After scaling, we apply Softmax to convert scores into attention weights. Softmax gives us a probability distribution, values between 0 and 1 that sum to 1. This has an important effect. High scores get emphasized, low scores get suppressed. The model makes decisive choices about what to attend to. For example, when processing, the cat sat on the mat because it was tired, the attention weights for it should heavily weight cat. That's what it refers to. The final step of attention combines the Softmax weights with the value vectors. We multiply each value vector by its attention weight and sum them up. This produces a context-aware output vector. Words with high attention weights contribute more to the output. Words with low weights contribute almost nothing. The result is that each position now contains information from across the entire sequence, weighted by relevance. Residual connections and layer normalization are crucial for training deep transformers. The residual connection adds the input directly to the output. Output equals sublayer x plus x. This helps gradients flow through the network without vanishing. Layer normalization stabilizes the activations, keeping them in a reasonable range. We apply this pattern after every sublayer, after attention, and after the feed-forward network. After attention, each position passes through a feed-forward network. It's a simple 2-layer network with a ReLU activation. Expand to 2048 dimensions, then compress back to 512. The key insight is that this network is applied identically to each position. There's no information sharing between positions here. That's the attention layer's job. The FFN adds nonlinearity and increases the model's capacity to learn complex patterns. After passing through all encoder layers, we have our final output. Each position now contains a rich, contextualized representation. The vector for bank and riverbank is different from bank and bank account. Context has been incorporated. These representations are passed to the decoder, which will use them to generate the output sequence. The encoder has done its job, understanding the input in its full context. Now let's look at the decoder. It generates output tokens one at a time, auto-regressively. The decoder has 3 key components. Masked self-attention prevents looking at future tokens. When generating word 3, you can only see words 1 and 2. Cross-attention connects decoder to encoder outputs. This is where the decoder looks at the input. The feed-forward network works exactly like in the encoder. Finally, a linear layer plus Softmax produces a probability distribution over the vocabulary. The decoder workflow starts similarly to the encoder. Output embeddings convert previously generated tokens to vectors, same 512 dimensions. Positional encoding adds position information. The decoder starts with a special start token and generates tokens one by one until it produces an end token. Masked self-attention is crucial for autoregressive generation. Unlike the encoder where every word can see every other word, the decoder masks future positions. When predicting position 4, positions 5 and beyond are hidden. This is implemented with a mask matrix that sets future positions to -infinity before Softmax, making their attention weights 0. Without masking, the model could cheat by looking at the answer while generating. Cross-attention is how the decoder accesses the encoder's output. Here's the key difference. Queries come from the decoder, but keys and values come from the encoder. This allows each decoder position to attend to all encoder positions. When translating "how are you" to Spanish, the decoder generating "estas" can focus on "are" and "you." This is the bridge between understanding and generation. The decoder's feed-forward network is identical to the encoder's. Two linear layers with ReLU in between, applied position-wise. And like the encoder, every sublayer, masked attention, cross-attention, and feed-forward has residual connections and layer normalization. This consistent architecture enables stable training of deep models. The final step is generating the actual output token. A linear layer projects from 512 dimensions to vocabulary size, say 10,000 possible words. Softmax converts these scores to probabilities. We select the highest probability token, add it to the decoder input, and repeat. This continues until we generate an end-of-sequence token. Transformers come in three main variants. Encoder-only models like BERT process the full input bidirectionally. They're excellent for classification, named entity recognition, and understanding tasks. Decoder-only models like GPT process left to right. They excel at text generation and completion. Encoder-decoder models like T5 use the full architecture. They're ideal for translation and summarization, where you need to transform one sequence into another. Most modern LLMs like GPT-4 and Claude are decoder-only, generation-focused. Now let's connect transformers to large language models. This is where the architecture scales to unprecedented sizes. A large language model is a transformer trained on massive amounts of text, billions to trillions of words. Large refers to both data and parameters. GPT-3 has 175 billion parameters. These are the weights learned during training. The training objective is simple: predict the next word. But at scale, this simple objective produces emergent capabilities: reasoning, following instructions, writing code. LLMs use transformers as their foundation, but the scale is what enables their remarkable abilities. Let's clarify the relationship between transformers and LLMs. Transformers are the architecture, the blueprint for how information flows. LLMs are specific models built using that architecture, trained at massive scale. Transformers can be used for many tasks beyond language: vision, audio, multimodal. LLMs specifically target language understanding and generation. Think of it this way: transformers are the engine. LLMs are high-performance vehicles built with that engine. Thank you for your attention. We've covered the complete journey from RNN limitations to modern LLMs. The key takeaways: attention enables parallel processing and captures long-range dependencies. The encoder-decoder architecture separates understanding from generation. Scaling this architecture gives us the powerful language models we use today. I'm happy to take questions.